Alright, graphing linear inequalities, so we know linear functions and we know inequalities and how those work, but graphing linear inequalities is quite a bit different, but it's also quite a bit the same as what we've been doing. So, feel confident, you got all the tools you'll need, but it is a new practice and a new type of problem to work with, so we're going to have to pay a little bit of attention. So here we go. Let's just first talk about this, and again, you don't have to write this, but I would appreciate you paying attention, and just because I'll use this as a means of explaining the notes we're about to see. I just want to use an XY chart, and I know that inequalities have infinite numbers of solutions, but so do linear functions. So let's just try and find some of those solutions. Let's find some points and graph them that make this true. For example, if I plug in 0 for x, 2 times 0 is 0. 0 minus 5 is negative 5. And y has to be greater than negative 5. What y is greater than negative 5? Oh, 0. So the origin is a point. What about 1? If I plug in 1 for x, 2 times 1 is 1, or 2 times 1 is 2, sorry. 2 times 1 is 2, 2 minus 5 is negative 3. What number is greater than or equal to negative 3? Well, 0 is greater than negative 3. Okay, what about 2? 2 times 2 is 4. 4 minus 5 is negative 1. What number is greater than or equal to negative 1? Oh, 0. But what other numbers are greater than negative 1 that we get on that side if we plug in 2? What other numbers are greater than negative 1? Greater than or equal to negative 1. Oh, negative 1 is greater than or equal to negative 1. Oh, positive 1. Oh, positive 2. These are all points that make this true. Let's see what happens when we graph them. We have 0, 0. We have 1, 0. We have 2, 0. But we also have 2, negative 1. We have 2, 1. We have 2, 2. This is really interesting. So we have not just a line, but it looks like it's going to be a whole area of the graph that is going to make this true. So that's what we're doing with graphing linear inequalities, is we're trying to find the portion of the graph that has solutions that make it true. So we're showing a whole bunch of different solutions on the graph just by shading in an area. So that's what we're doing, and let's talk about how to do it and why it makes sense. So the notes are: inequalities typically have an infinite number of solutions. So that's the normal inequalities that we've worked with in the past. Now, linear inequalities have a bigger infinite number of solutions, which is really interesting. So the reason there is because not only are we drawing a number line that extends infinitely in both directions, and in one direction we have all the solutions, but we could draw an infinite number of number lines, and they all extend infinitely in one direction with solutions. And we'll see what that looks like in a second. So how are we going to graph them? How are we going to find all these big infinite number of solutions? Well, first we're going to find points for the corresponding linear equation. So we're going to ignore that it's an inequality. We're going to say, what if this was a linear equation? What if it was an equal sign instead of an inequality symbol? Then we're going to connect the points with a solid line if all these points would make it true, and that's if it says y is greater than or equal to, or less than or equal to. If that's the case, then the points on the line would make it true, because it could be equal. It could be the linear equation. But if they couldn't be, if the linear equation is not a set of solutions, that would be if we have the less than sign or the greater than sign. So we're going to find some points for the linear equation. We're going to connect them with a solid line if they work for the inequality. We'll use a dotted line if they don't work. Now that kind of splits our graph. After that, we need to find out which side are all the correct solutions on. So we're going to choose a test point on either side of the line. We'll choose something that is obviously not close, but on one side clearly. And if the test point is a solution, we'll shade that side. If it works, if it's not a solution, we'll shade the other direction. So let's put it in practice. Hopefully you have the notes. Hopefully they make sense, but they're going to make much more sense when we get to work. So let's check it out. Y is greater than negative x plus 3. It says graph the linear inequality using the given test point. I didn't give you a test point, but I'm going to do it real quick. Let's say the test point is negative 3, 2. That'll be fine. Okay, So we said that the first step was just to treat it like a linear equation or a linear function. So to use an XY chart. And we'll say if this were a linear equation, I could plug in -1, 0, and 1, and now I get some corresponding y values. And I'll do -2. Let's do 5 points just because. Okay, so if -2, if I plug in -2, what's the opposite of -2? It's +2. 2 plus 3 is 5, so that's 1 point. If I plug in -1, what's the opposite of -1? 1. 1 plus 3 is 4. 0, the opposite of 0 is 0. 0 plus 3 is 3. 1, negative, the opposite of 1 is -1. -1 plus 3 is 2. We can see a pattern here. This is a constant slope. It's because it's linear. The opposite of 2 is -2. -2 plus 3 is 1. So we got 5 points here. So -2, 5, -2, 3, 4, 5. That's a point. -1, 4, 0, 3, 1, 2, and 2, 1. These are all points. The second step said if these points work, if we had that little equal sign or equal to sign underneath, these points would work because the inequality would include the linear function. Then we use a solid line. If not, in this case, they don't work because they would be equal. One wouldn't be greater than the other. They don't work, so we need to use a dotted line because, again, we only shade things that make an equation true. So I'll use a dotted line, and it'll be poorly drawn as ever, but that's okay, and you'll forgive me. So we use a dotted line, and that kind of splits our graph. And we know that one side is going to be all the ordered pairs that make the inequality true, and one side is all of them that don't make it true. So we have to find out which is which. So let's look at -3, 2. We can go -3 up to 2. All right, let's test this point and see, does this point and all the points on this side make it true or not? Well, if I put in -3, the opposite of -3 is 3. 3 plus 3 is 6. And we'd have 2 is greater than 6. Is that true? That is not true. So I know that this is not a solution. We need to shade all the solutions, which happen to be above and to the right on the opposite side. We're shading away. So that's all. These are all the huge infinite number of ordered pairs that would make this inequality true. So hopefully that made some sense of the notes we took. Let's see another example. This one says graph the solution set. Again, we can just start by graphing the linear equation, but this time it's given to us in standard form, so let's find some different points. The greatest or easiest points to find in standard form, I think, are the x and y intercepts. So the value of y when x equals 0. If x equals 0, we have -2y is less than -3. I could divide both sides by -2. We have y is equal to, if we're treating it like a linear equation, -3/2. What about the value of x when y is 0? Well, when y is 0, we just have 4x is less than or is equal to 3, so x would be 3/4. Okay. Is that true? Yeah, x would be equal to 3/4. Now, we can graph just using these two. So I'm gonna treat each. We'll go y's by 1/2, and this will just make it easy to connect. Y's by 1/2, x's by 1/4. So 0, -3/2 would be 0, -1/2, -2/2, -3/2. That's 1 point. And then our x-intercept is 3/4, 0. So 1/4, 2/4, 3/4, 0. Now, are these points, do they make it true? Well, it could be equal. And these points are from the equation where it is equal. And this includes that equation. So yes, we need to use a solid line. So I'll just connect them like normal. And we know that everything on this line is a solution. But not just everything on this line, also an entire side in addition. What test point do we want to use? We need to use a test point. Again, that's the last step, is to figure out which side should be shaded with all the correct solutions. And I like to use the test point 0, 0. It's usually pretty obvious, so let's look at it. Is this a solution? That would be 4 times 0 minus 2 times 0 is less than or equal to 3. So that would be is 0 minus 0 less than or equal to 3? And the answer is yes. So this is a solution as well as everything on this entire side. So there we go, we're shading the correct side, and you might say to yourself, this algebra stuff looks kind of messy. And graphing linear inequalities does look kind of messy. You can do it nicer with a pencil, but the whole idea of it is pretty funny. We're graphing a huge infinite number of solutions by just shading a space on the coordinate plane. All these combinations of points of x and y values make that linear inequality true, and we just showed them all. Oh, I gave us one more, so let's do it real quick. First, I'm going to graph the line of the equation. So what is this? This is point-slope form. The slope is 6. What's the point? It is 3, negative 18. We're going to need to choose a different y. Let's choose negative 2 for this. So at 3, 1, 2, 3, negative 18. So I went down 9, but remember the scale tells me that each one goes down 2. So that's actually 3, negative 18, and my slope is 6. So as I go 1 to the right, I should go up 2, 4, 6. As I go another 1 to the right, I should go up 2, 4, 6. As I go one more to the right, I should go up 2, 4, 6. All right. Now, dotted line or solid line? Well, it couldn't be equal. So the points I just found are actually not solutions. So I just need to use this as the dotted line. This is the barrier, and everything on the barrier does not make it true. Okay, now finally, test point 0, 0. Does it make it true? Is 0 plus 18 greater than 6 times 0 minus 3? 0 minus 3, I don't know why I put that comma, it's okay. Is 18 greater than 6 times negative 3? Is 18 greater than negative 18? Yes, it is. So this is a solution as well as everything on the test point side of our barrier, that dotted line. So again, we graphed another set of solutions, another solution set, and it's an entire side of the graph. All of these points, no matter where it is, negative 4, 20, that would work because it's shaded. So we're all good. I'm going to leave you with some to do on your own. The first one says, graph and determine if the given point is a solution. Once again, I didn't give you a point, so here it is, 220. And then the second one just says graph the solution set. So you're going to be able to use your own test point on that one. Best of luck. You guys are going to dominate. I'll see you soon.